In this video, we're going to go through an example reaction that uses Le-Chatelier's principle. So what we're going to do is we're going to apply Le-Chatelier's principle to look at various changes to this reaction when we perturb our reaction from equilibrium. Just as a reminder, what do I mean when I say this reaction is at equilibrium? So what that means is we have a reversible reaction, we have the forward reaction, which has some rate k forward. The reverse reaction has some rate k backward. And at dynamic equilibrium, these rates are equal to each other. So all of the concentrations are going to stay constant. And then what we do is we decide to see what happens when we add some carbon dioxide gas. If we add carbon dioxide gas, the concentration of carbon dioxide will go up. Or you can think about it as a partial pressure going up. And Le-Chatelier's principle tells us that if we had a reaction at equilibrium and then we perturbed it by adding more CO2, it will shift to try to reduce the effect of that change. So it'll favor the reverse reaction. So if we add CO2, what happens is we favor our reactants. Another way we can see this is by looking at the equilibrium constant for this reaction. So we can write our equilibrium constant K, where this is a capital K. It's kind of confusing, but I will try to make this look like a capital K. And we can write it in two ways. We can write it in terms of the concentration, the molar concentration. And if we write Kc, the expression will be the product concentration, so our CO2 gas concentration, and that's it. Because when we write out Kc, we write out concentrations of gases and we write out concentrations of solutions, but we don't include solids. So Kc is just the concentration of CO2 at equilibrium. And I'm going to write an EQ there just to show that's the equilibrium concentration. And I said you can also write it in terms of partial pressures. So there's our fancy capital K with a P subscript, which means that instead of concentrations, we're writing everything for gases in terms of partial pressures. So we have the partial pressure of CO2. And again, that's it, because everything else is a solid, so we don't include those in our equilibrium expression. So writing these expressions out will be really helpful for our second condition. So we're going to think about what happens when you increase the volume of our container. We can rewrite the partial pressure actually in terms of the volume. So if you use the ideal gas law, the partial pressure of CO2 is equal to the moles of CO2 times RT divided by the volume. And similarly, we can rewrite molar concentration in terms of moles divided by volume. If we increase the volume of our container, increasing the volume, since it's in the denominator, will make our pressure go down. So our partial pressure of CO2 will go down, and we won't be at equilibrium anymore. And same for the concentration. Since our perturbation is decreasing the carbon dioxide concentration, Le-Chatelier's principle says that our reaction will try to counteract that change. It'll try to get back to equilibrium and try to get the CO2 concentration back up. And so it'll have to favor products. Our reaction will favor the products to try to get the CO2, moles of CO2 back up so that we get back to the equilibrium concentration of CO2 and the equilibrium partial pressure. The third change we're going to look at is what happens when you add argon gas. So argon gas is an inert gas. We don't expect it to react with anything. One thing that'll happen when you add the argon gas is it will increase the overall pressure of your container. So it'll increase the total pressure. Oops. But that actually doesn't tell us what it does to our equilibrium. Let's look back at our equilibrium expressions, Kc and Kp. We can see that the partial pressure for Kp only depends on the moles of our CO2 and our volume, since we didn't change the moles of CO2, and we also didn't change the volume. Even though we increased P total, the partial pressure of CO2 stayed the same. So that means we didn't perturb our reaction from equilibrium, and since we didn't perturb it from equilibrium, there'll be no shift. We are still at equilibrium, the concentrations will still stay the same. What happens when we add more calcium carbonate? So that's our starting material, and it is a solid. Our equilibrium expressions are determined by our CO2 concentration. So adding more calcium carbonate, which is a solid, isn't actually going to perturb our reaction from equilibrium. Our reaction is still going to be at equilibrium, and we will get no shift in concentrations. We're actually going to look at one more thing. We're going to think about what happens when you add a catalyst. Let's say we want to speed up this reaction. We can envision what's going on here when we add the catalyst by using an energy diagram. So if we have an energy diagram, we have energy on the y-axis, and we're looking at the difference in energy between our reactants, or starting materials, with our products. And I just sort of made up these relative energies. The way that I have this drawn here, we can see that our product is lower in energy than our starting material, and our forward rate, Kf, which is up here, Kf is determined by the size of this activation barrier between our starting material and our transition state. Our backward rate, Kb up here, our backward rate is determined by the size of this energy barrier. So the difference in energy between the product and our transition state. If we add a catalyst to our reaction, we can think about it as lowering the activation energy for our reaction. And that means we have a lower energy barrier for our forward reaction. So our forward reaction is going to get faster, but it's also going to lower the rate of our backward reaction. So K backward, or Kb, is also going to speed up. And since it speeds up both the forward and the backward reactions, adding a catalyst also won't perturb your reaction from equilibrium. So adding a catalyst will result in no shift in concentrations. So the main things to remember from this problem, I think, the things that I find most tricky anyway, are that adding an inert gas, it'll increase your total pressure, but it won't actually change any of your partial pressures, so it won't shift your reaction from equilibrium. And the same thing is true for solids and catalysts. So all of those three things, inert gases, solids, and catalysts, will not shift your reaction from equilibrium.
Let's say we had the reaction molecule A plus molecule B is in dynamic equilibrium with molecule C plus D, which just means that the rate of the forward reaction is going at the same rate as the backward reaction or the reverse reaction. There'll be some equilibrium concentrations of A, B, C, and D, and we can figure out what the equilibrium constant is if we want. And I'll say it again, I've said it like 4 times so far. The fact that the forward reaction rate is the same as the backward reaction rate doesn't mean that all of the concentrations are the same. The concentrations themselves of each of the molecules could be very different. They're just not changing anymore because the forward and backward rates are the same. Now, given that we're at equilibrium now, what's going to happen if I add more A to the system? More A. So remember, it was in equilibrium. It was in equilibrium. The concentrations were constant, but now all of a sudden I'm adding more A to the system. So now the odds of an A and a B particle, even though I'm not adding any more B molecule to the system, the odds are slightly higher that an A and a B are going to collide in just the right way. So the forward reaction is going to be more likely. So if we add more A to the system, you're going to have more A's. They're going to bump with more B's. So the B's are actually going to go down a little bit, right? Because more B's are going to be consumed. And even more important, the C's and D's are going to definitely be increased. And the way it would really happen, you would add more A, those A's would bump into some more B's, and so this forward reaction, all of a sudden its rate would go faster than this backward reaction, so the reaction would go in that direction. Then you'd have more C's and D's, and maybe some of those are more likely to bump and go back in this direction, and eventually you would reach a new equilibrium. But the bottom line is you'll be left with more A, a little bit less B because you didn't add more B. So more B is going to be used to consume with those extra A's you just added. And then those are going to produce more C's and D's in equilibrium. And you can imagine if you added more A and more B, let's say if you added more B as well, more B, then both of these are going to, then the reaction is going to go into the forward direction even more. Even more. I don't think this is, an amazing insight of the world. I think this is kind of obvious that if you stress this reaction by adding more on this side, that naturally it's going to move in the direction that relieves the stress. So if you add more A, you're going to have more A's bumping with B's and go in that direction, maybe consume a little bit more B's. If you add more both, the whole thing's going to go in that direction. Likewise, let me rewrite the reaction. Do it in different color. A plus B, dynamic equilibrium, C plus D. If I add, it's too dark. If I add more C, I think you get the point here. What's going to happen? Well, that's going to drive A and B up, and it's maybe going to consume a little bit of extra D. And then if you added more C and D, then of course it's going to produce a lot more A and B. And this idea, it seems pretty common sense, but there's a fancy name for it. It's called let me put a capital L, Chatelier's principle. Chatelier's. If you've watched enough of these videos, I have to be careful with my spelling. Principle. And all it says is that when you stress a reaction that's in equilibrium, the reaction will favor the side or one side of the reaction to relieve that stress. So when they say stress the reaction, that's like adding more A. So the reaction is going to move towards the forward direction to relieve the stress, the quote-unquote stress of that more A. I mean, that's not stress in its traditional way of thinking about stress, but that is a kind of stress. You're somehow changing it relative to it. It was nice and comfortable before in a nice stable environment. So given Le-Chatelier's principle, let's think of some other situations. Let's say if I had, A plus B plus some heat. And that produces some C plus D. And, maybe it produces some E as well. So if I were to add heat to this system, what would happen? So if I were to add heat, so in order for the reaction to progress in the forward direction, you need heat. The more heat you have, the more likely you're going to progress in the forward direction. So Le Chatelier's principle will say we're stressing this reaction by adding heat. So the reaction will favor the direction that relieves that stressor. And so to relieve that stressor, you have more of this input. So you're going to consume more A. So the stable concentration of A, once we reach equilibrium, will go down. B will go down because they're going to be consumed more. The forward reaction is happening more. And then C, D, and E would go up. Now, if you did the opposite, let me erase what I just did. Let's say instead of adding heat, you were to take away heat. So let's say you were to take away heat. Let me make sure my cursor is right. So if you took heat away from the reaction, what will be favored? Well, then you're going to be favoring it in the other direction because then there'll be less heat here. I mean, all of this is together. There'll be less heat for this reaction to occur. So this rate will start dominating this rate over here, right? If you take away heat, the rate of this reaction will slow down. This one will be bigger, and so you'll have more movement of concentration in that direction, or the reverse reaction will be favored. Now let's think of another stressor, pressure. Now imagine that we mentioned the Haber process before, and this is the reaction for the Haber process. Nitrogen gas plus 3 moles of hydrogen gas in equilibrium with 2 moles of ammonia gas. Now, what's going to happen if I apply pressure to this system? I'm going to apply pressure. So if you think about what happens with pressure, everything all of a sudden is getting is squeezed, although it's not necessarily, the volume isn't necessarily decreasing, but something is somehow making all the molecules want to be, or forcing them to be closer together. Now, when things are getting closer together, the stress of the pressure could be relieved as if we end up with fewer molecules. Think about it this way. Think about it this way. PV is equal to nRT. We learned this multiple times, right? And let's say we could write P is equal to nRT over V. Now, if we increase the pressure, right? If we increase the pressure, how can we relieve that? Remember, the Le-Chatelier's principle says that whatever is going to happen is going to relieve the stressor. The reaction is going to go in the direction that it relieves it. Well, if we lower the number of molecules, then that will relieve the pressure, right? You'll have fewer things bouncing against each other. So if we lower the number of molecules, where you can kind of view it. I mean, this is, it's not, I shouldn't have written it this way because it's not quite an equation, but I want you to think of it that way. If I'm, let me erase this. This probably wasn't the best intuition. If I have a container, nope, too shocking. Nope, same thing. I have a container and I'm applying pressure to it. And in one option, I could have two molecules. Let's say I could have 4 molecules in some volume. And in another situation, let's say they get merged and I only have 2 molecules, right? And either of these, the reaction can go between these 4, could merge to make 2 molecules. And let me use this example up here. Let's say this nitrogen molecule is this blue one here. Actually, let me do it more different color. This brown one right here. It can merge with 3 hydrogen. It could produce this. So this is another way of writing this reaction, maybe in a more visual way. Now, if I'm applying pressure to this system, so pressure I just imagine is kind of, more force per area from every direction. Which of these situations is more likely to relieve the situation? Well, the situation where we have fewer molecules bumping around, because it's easier to kind of apply or I guess squeeze them together than when you have more molecules bumping around. This is, I'm doing this very hand wavy, but I think it gives you the intuition. So if you apply pressure to the system, if pressure goes up, you're applying, this doesn't mean pressure goes down. This means pressure is applying to the system. But the pressure is going up, what side of the reaction is going to be favored? The reaction is going to be favoring the side that has fewer molecules. And this side has 2 molecules, although there'll be bigger molecules, obviously, because it's not like we're losing mass in one direction or the other, as opposed to this situation where we have 4 molecules, right? 1 mole of nitrogen gas and then 3 moles of hydrogen. And just to bring this all back to the whole idea that we saw earlier with the kinetic equilibrium, is let's just imagine a reaction like this, and just show that it works with this Le-Chatelier's principle is consistent with everything we've learned with equilibrium constants. So let's say we had the reaction 2 moles or the coefficient of 2 A's in the gaseous form plus B in the gaseous form is in equilibrium with C in the gaseous form. And let's say initially we're in our first equilibrium, is our concentration of A is 2 molar, or our molarity is 2. Our concentration of B is 6 molar concentration. And then our concentration of C is 8 molar. So what's the equilibrium constant here? The equilibrium constant here is the product concentration of C, that's 8 molar, divided by 2 molar squared, because of this, 2 squared, times 6, which is equal to 8 over 4 times 8 over 24, which is equal to 1/3. Now, let's say we were to add more A. And I'm not going to say exactly how much, we could actually get quite complicated with the mathematics, but let's say after adding more A, we have a new concentration. Now, let's say our concentration of A is 3 molar. You might say, hey, Sal, didn't you add 1 molar? No. I actually added probably more than 1 molar. What happens is I add whatever I added that will push the reaction towards the right direction or towards the forward direction. And so some of it will get consumed and go in that direction, but the whatever's left over is here. So I might have added more than 1 molar concentration to this system. Whatever was more extra beyond the 1 was consumed, and I'm just left with this equilibrium concentration of 3. So I didn't necessarily add 1. I could have added more than that. And let's say that our new equilibrium for C is 12 molar, right? Which is consistent with what we say. We should be producing, if we add some A, if we're adding A, then our concentration of C should go up. And the intuition is that the concentration of B should go down a little bit because a little bit more B is going to be consumed because it's going to be colliding with, or it's more likely to collide with more A particles or A molecules. So let's see what B's new concentration is. So remember, the equilibrium constant stays constant. So our equilibrium constant is now going to be equal to the concentration of C. Right, that was the reaction. So it's 12 molar. Oh, whoops, 12 molar. I don't have to write the units here. Divided by our new concentration of A. That's 3. But remember the reaction. The coefficient on A is 2, so it's 3 squared. Times the concentration, the new concentration for B. Right, there's no coefficient here, so I don't have to worry about any exponents. And let's just solve this. So you get 1/3 is equal to 12 over 9b. So if we just cross multiply, we get 9 times the concentration of B is equal to 3 times 12, which is 36. And so divide both sides by 9. The new concentration of B is 4, or 4 molar. So B is equal to 4 molar. So that makes sense. We added some more A to the reaction. So we started with 2A, 2 molar of A, 6 molar of B, 8 molar of C. When we added more A, at the end, we added a bunch. It went in that direction. Maybe it went back and forth a little bit, but it stabilized at 3 molar of A, 12 molar of C. So C went up. So that definitely went up. And notice, some more, our stable equilibrium concentration of B actually went down. And this is consistent with what we were saying, that the reaction moves in that direction, more C gets produced, a little bit of B gets consumed. So anyway, hopefully you're fairly comfortable now with the whole notion of stressing a reaction and Le-Chatelier's principle.